What's up everyone, welcome back to Wonders of the Universe, back with another video, and today we're diving into the vast universe, an expanse so immense that it defies our understanding. It's a concept that stretches the limits of human comprehension, challenging our very perception of reality. When we gaze upon a star-filled night sky, we only glimpse a tiny fraction of what's out there, a mere speck in the grand tapestry of the cosmos. The universe extends far beyond our ability to fully grasp, yet we strive to understand its immensity, driven by an insatiable curiosity. How big is the universe? This question has intrigued and puzzled humanity for centuries. It's a question that has captivated astronomers and cosmologists for centuries, driving them to explore the farthest reaches of space and time, seeking answers in the stars. The universe is not just big, it's unfathomably big, a scale so vast that it boggles the mind. Our minds struggle to conceptualize its true scale, grappling with numbers and distances that seem almost abstract. To put things in perspective, consider the Earth, a planet we perceive as vast, teeming with life and landscapes. Yet in the grand scheme of the universe, Earth is but a tiny speck of dust, almost insignificant in the cosmic ocean. Our planet is dwarfed by the Sun, a star so massive that it could hold over 1 million Earths within its fiery embrace. And the Sun is just one of billions of stars in the Milky Way galaxy, our cosmic home, a vast collection of stars, planets, and cosmic wonders. Even the Milky Way, a swirling disk of stars and gas spanning hundreds of thousands of light-years, is just one galaxy among billions upon billions scattered throughout the observable universe, each with its own mysteries and wonders. When we talk about the size of the universe, we often refer to the observable universe, which is a fascinating concept in itself. This observable universe is the portion of the cosmos that we can currently observe from Earth, using our most advanced telescopes and instruments. It's limited by the speed of light and the age of the universe, which means we can only see as far as light has traveled since the beginning of time. Imagine standing on a ship in the middle of the ocean, surrounded by water in every direction. You can only see as far as the horizon, where the sky meets the sea, creating a boundary for your vision. Similarly, the observable universe is like a cosmic horizon beyond which we cannot see, no matter how powerful our telescopes are. Light from objects beyond this horizon has not had enough time to reach us since the Big Bang, the event that started it all. The observable universe is estimated to be about 93 billion light-years in diameter, a mind-boggling distance. This means that light from the most distant objects we can see has been traveling towards us for about 13.8 billion years, which is the estimated age of the universe. However, it's crucial to remember that the universe is not static, it's dynamic and ever-changing. It's constantly expanding, which means the actual size of the universe is likely much larger than what we can currently observe, stretching far beyond our current cosmic horizon. As our technology advances, we may one day be able to peer even further into the depths of space, uncovering more of the universe's secrets and expanding our understanding of the cosmos. Until then, the observable universe remains our window into the vast, mysterious expanse that surrounds us, a reminder of how much there is still to discover. One of the key pieces of evidence supporting the Big Bang theory is the cosmic microwave background, or CMB. This discovery has revolutionized our understanding of the universe's origins and its subsequent evolution. This faint afterglow of radiation permeates the entire universe, providing a cosmic backdrop that tells the story of the universe's birth and growth. It's a relic of the intense heat and energy present in the early universe, just a few 100,000 years after the Big Bang. During this period, the universe was a hot, dense plasma of particles. In 2013, the European Space Agency's Planck space mission provided the most detailed map of the CMB ever created. This mission has been pivotal in enhancing our understanding of the universe's structure and composition. By studying the tiny temperature fluctuations in the CMB, scientists have been able to determine the age of the universe with remarkable precision, pegging it at about 13.8 billion years old. These fluctuations also reveal information about the universe's rate of expansion and its overall geometry. The CMB provides us with a snapshot of the universe in its infancy, a time when it was much hotter, denser, and more uniform than it is today. This snapshot is like a baby picture of the cosmos, showing us how it looked long before stars and galaxies formed. As the universe expanded and cooled, this radiation stretched and cooled, eventually becoming the faint microwave glow we detect today. This glow is a crucial piece of the puzzle in understanding the universe's history and its ongoing evolution. The universe is not static, it's constantly expanding. This means that galaxies are moving away from each other, like dots on a balloon being inflated. The farther away a galaxy is from us, the faster it appears to be moving away. This expansion was first observed by astronomer Edwin Hubble in the 1920s. He noticed that the light from distant galaxies was redshifted, meaning its wavelength was stretched towards the red end of the electromagnetic spectrum. This redshift is similar to the Doppler effect we observe with sound waves. Just as the pitch of a siren drops as it moves away from us, the wavelength of light from a receding galaxy is stretched, causing it to appear redder. Hubble's discovery revolutionized our understanding of the universe. It implied that the universe was not eternal and unchanging but had a beginning and was evolving over time. The enigma of dark energy. While the expansion of the universe is well established, what's driving this expansion remains one of the biggest mysteries in modern cosmology. Scientists believe that a mysterious force called dark energy is responsible for this accelerated expansion. Dark energy is thought to make up about 68% of the total energy density of the universe. Unlike gravity, which pulls things together, dark energy seems to be pushing things apart. It's as if there's an invisible force embedded in the fabric of space-time itself, causing the universe to expand at an ever-increasing rate. The discovery of dark energy has profound implications for our understanding of the universe's fate. If dark energy continues to dominate, the universe will expand forever, becoming increasingly cold and diffuse. Galaxies will be pushed farther and farther apart, eventually becoming isolated islands in the vast cosmic void. Cosmic yardsticks, measuring astronomical distances. Measuring distances in space is a complex task. Astronomers have developed various techniques to determine the distances to celestial objects, each with its strengths and limitations. One common method is using standard candles, objects with known luminosities. By comparing the apparent brightness of a standard candle to its known luminosity, astronomers can calculate its distance. Supernova, the explosive deaths of white dwarf stars, are particularly useful standard candles because they have very consistent luminosities. Another method is using cosmic distance ladders. This involves building a chain of distance measurements, starting with nearby objects whose distances can be measured directly, and then using those measurements to calibrate the distances to more distant objects. The shape of the universe, a cosmic puzzle. The shape of the universe is another fundamental question that cosmologists grapple with. Is it flat, spherical, or saddle-shaped? The answer has implications for the universe's ultimate fate and whether it's finite or infinite. Current observations suggest that the universe is very close to being flat, meaning it has no overall curvature. Imagine a beam of light traveling through space. In a flat universe, the beam would continue in a straight line forever. In a spherical universe, the beam would eventually converge, while in a saddle-shaped universe it would diverge. The flatness of the universe is a puzzle because it suggests a remarkable degree of fine-tuning in the early universe. Beyond the observable, the true extent of the cosmos. While the observable universe provides us with a glimpse of the cosmos, it's important to remember that it's just a tiny fraction of the entire universe. The actual universe could be vastly larger, perhaps even infinite. One way to think about this is to imagine the universe as a giant loaf of raisin bread. The observable universe is like a small section of that bread that we can see. As the bread rises, representing the expansion of the universe, the raisins, representing galaxies, move farther apart. However, there could be countless more raisins, galaxies beyond our slice of bread, hidden from our view. An everlasting quest for knowledge. The quest to understand the size and nature of the universe is an ongoing journey. As our telescopes become more powerful and our understanding of the cosmos deepens, we continue to push the boundaries of our knowledge. The universe is a place of wonder and mystery full of endless possibilities. From the smallest subatomic particles to the largest cosmic structures, the universe is a tapestry woven from the threads of physics, astronomy, and cosmology. As we continue to explore the cosmos, we are constantly reminded of our place in the grand scheme of things. We are but a small part of something much greater than ourselves, a universe that continues to inspire awe and wonder. If you love space facts, hit that like button and subscribe for more cosmic wonders. Stay curious and keep exploring the wonders of the universe.